Okie dokie, maybe we can get started. My plan for today is to do a couple of things. First, a kind of little review of some of the things that have happened to this subject, linking combinatorics, geometry, and scattering amplitudes over the past couple of years, where especially over the past couple of years, something sort of conceptually new has happened, which I think is very important and is going to be a theme for, or common theme for a lot of these lectures, which is that we're beginning to see at least one possible answer to the grand underlying question that motivated a lot of these investigations, which is to think of scattering amplitudes as the answer to some natural, somewhat perhaps abstract and alien, but nonetheless very natural and beautiful kind of mathematical question, directly in the space where they live, directly in the space of on-shell kinematical data, rather than as answers to questions that are formulated in auxiliary spaces. And I will say a little bit more about that in a second. But this sort of basic point of view really first came into at least our own consciousness in the work with Hugh Thomas and Gara about a couple of years ago, thinking about a more intrinsic definition of what the amplituhedron is itself. In many ways, the amplituhedron is the kind of fanciest version of the story. It's the most sophisticated, intricate version of the story. There's a simpler version of the story that doesn't involve curvy geometries and so on, just involves ordinary polytopes and cluster polytopes, and that has to do with the physics of phi-cubed scattering amplitudes. Okay, so the amplituhedron has to do with gluons, or at loop level at equal 4 super Yang-Mills. Cluster polytopes have to do with the physics of biadjoint phi-cube theory. But this basic point of view that you're looking for some kind of object or question in kinematic space is basically going to be identical between these two stories. And one of the things which I found very striking is that thinking about this subject from this lens now brings all the different aspects of or many of the different aspects of physics of scattering amplitudes, n equals 4 super Yang-Mills, phi-cubed amplitudes, string amplitudes, all under a common rubric. They're all basically in exactly the same intellectual playground. And we're going to see that in these lectures. So that's one of the things that I want to do is highlight that fact. So in this lecture, we'll talk about amplitude. The next lecture, we'll talk about biadjoint phi-cube theory. The lecture after that, we'll run into string amplitudes, all in one sort of one sweep of thoughts. Okay. So one aspect of the lecture is going to just be a review of some of these ideas from a couple of years ago. But really, in the spirit of this workshop, I want to do two other things. One of them is just present all kinds of open problems related to these things as we go. So I'll be throwing out many things which are threads that have barely started to be developed. And many of these things have just been discussed in this workshop in the past couple of weeks. Okay, so the past couple of weeks or a month. So some of these ideas are going to take some time to develop, and of course, anyone who has anything to say or think about them is welcome to do so. Some of the newer things that I'll talk about that aren't just a review are based on, I think, something like 4 papers that, God willing, will come out at some point this year, before the end of the year. But I will be interspersing them with new things as we go. Things that have just come up in the past couple of weeks or a month. All right, so in this lecture, we're going to talk about the amplituhedron, and let me again remind what the sort of general question is. The general question is that we have some particles coming in and out from infinity. We can eventually imagine all the lines as incoming, and there's some amplitude for this process, and the experimentalist who lived at infinity doesn't know that there was all this stuff going on inside the space-time, that there are particles there, they bang into each other, this happens, that happens, all these loops happen, all this stuff that happens on the inside is invisible to this experimentalist at infinity. All they see is the outcome of the experiment. And so we want to know what question directly in the objects the experimentalist has access to, which are the data that labels the on-shell scattering processes. What question has as an answer that amplitude that they measure? Okay? Of course, they don't directly measure an amplitude. This is a slightly imaginary experimentalist, but that's the question that we're interested in. And of course, the conventional answer to this question already involves an auxiliary space. The auxiliary space is space-time. The interior of the space-time is the auxiliary space. And you can fill in the inside of this picture with a conventional picture of Feynman diagrams and processes and complicated things that happen on the inside and summing all the possible ways things could have happened. So that's a conventional answer. Okay? It also involves some auxiliary space. It's just we're very familiar with it. We feel that we live in it. Okay? It's space-time. Okay, so the first auxiliary space is space-time. But over the past 50 years, there have been really two other examples of auxiliary spaces that we've come up with. The first one, sort of famously 50 years ago, is the string worldsheet. String theory, the string worldsheet. And here you do a totally different computation. You don't see the inside of the space-time. Instead, you imagine that you have all the incoming particles are sort of inserted as vertex operators. Let's say you're doing open string scattering on the boundary of some worldsheet, and you calculate a correlation function for these vertex operators in this auxiliary two-dimensional quantum field theory, and the answer to that question you interpret as a scattering process in space-time. Okay, so this is the second place. It's not space-time, but you do the computation there, and you get the answer. The third thing, more recently, is the story of the Amplituhedron, which is also lives in some auxiliary space. And let me just very briefly, yes?
Do we impose any asymptotic infinity condition or space-time?
Well, here, when we're talking about, when we do this calculation, the vertex operators that we talk about look like plane waves. They look like e to the I kx. And so that's how we're putting in the information that it's a scattering question. Okay, so, but nonetheless, it's done. It's a question that's asked on this auxiliary worldsheet. All right. Now, so this is already a little bit further from space-time, but after a little bit of work, you realize that what you're really doing here are thickened versions of ordinary Feynman diagrams. So it's not quite as far apart from ordinary space-time as it appeared at first, although it's definitely not the same. Okay, so it's now with Amplituhedron, we're quite a bit further from something that looks like an ordinary space-time, but still, it's something that naively lives in an auxiliary space. So the tree Amplituhedron is defined as some subset of the space of k-planes in k plus 4 dimensions, or k plus m dimensions in general. So alpha runs from 1 to k, I runs from 1 to m. We imagine that these z's are auxiliary data. So they're external data, sorry. And we have to assume that this external data is positive, so all of these k plus m minors of this Z matrix are positive in the sense of total positivity talked about yesterday. But they're fixed, but the C's span over the entire positive Rachmanian. So all of these CA1 through CAK, all of these minors are positive, and you vary over all of these. So if you vary over all of these, you carve out some subset in the space. This lives in the space of k-planes in k plus m dimensions. And this is the Rachmanian generalization of a polytope. And really more precisely, since we're demanding this external data has this positivity property, directly it's a generalization of this thing with an ordering on the Z and the positivity property is a generalization of the Rachmanian generalization of the cyclic polytope. And if you're not familiar with any of these things, in a sense, you don't need to worry about it, because we're shortly going to give a different definition for what it is. That's more intrinsic. But just to connect, the kinematic space here, this has to do with n equals 4 super-Yang nodes. The naive kinematic space, for n equals 4 super-Yang mills is just, I have the momentum twistor variables. So if you don't know what they are, if you're a mathematician, you know what they are. They're just n four-dimensional vectors. That's it. Okay? N real, n four-dimensional vectors in general. It's supersymmetric, so we also have these Grassmann cousins. So these are four-dimensional vectors. I also have Grassmann cousins, and I'll use the same 4, it just runs from 1 to 4. So that's the external data. And so you have to build out of these some function that depends on these z's and the etas. That's our goal. And the amplituhedron relates to that almost directly, but there's some slightly indirectly, because what we're supposed to do is look at a canonical form in this y space. So here in this y space, there's some region, some sort of curvy generalization of a polytope. So in y space, there's some region, which is the amplituhedron. There's a canonical form that has the property, so it depends on y, and it depends on this external data. I'll call it some ZA. Okay, and this canonical form has the property that it has logarithmic singularities on the boundaries of the amplituhedron. So you see there's a little bit of a mismatch. On this side, we have the space of k-planes in k plus m dimensions. M would be 4 for the physics applications. Okay, so if we're talking about n equals 4, we have the space of, so this is a top form on G, k plus m. M would be 4 for physics. So there's a y here, and also the z's aren't 4 vectors. The z's are like 4 plus k vectors. Okay, so there's maybe 4 things up here, but there's k additional components, zeta 1 through zeta k. Okay. So there are 2 things we have on this side that we don't have on this side. Here we just have 4 vectors as well as this annoying supersymmetry stuff. Here we have a k-plane in k plus 4 dimensions, and we have k extra components to this external data that we're talking about. And these things sort of cancel each other. So the way we're supposed to interpret going from here to there is that I'm supposed to imagine projecting this external data ZA through Y. So what that means is that you can imagine that you bring this k-plane in k plus m dimensions to a form where it has some identity block downstairs and 0, so it has some k by k identity block and m zeros up here. And if you do that, the z's would look like some m-dimensional z's up here, and then a bunch of extra components, and you're supposed to make these extra components infinitesimal. This is where all the Grassmann stuff lives. So I'm not going to go through this in any detail, but this is supposed to be an object that has Grassmann weight 4k in these variables, and all that information about the extra, all this information about the k and the Grassmann variables are shoved in the extra components of this external data. The actual data you see, the actual bosonic data you see, is just the projection of these z's through y. Okay, so the y, this k-plane in k plus m dimensions, is sort of allowing me to bosonize the supersymmetry, to sort of divide up the part of z that is the bosonic part we like, and the rest of it is thought of as being infinitesimal in some appropriate Grassmann sense. And then you have to do a little operation to this form to extract from this canonical form the amplitudes. And if that sounds a little bit complicated, good, because we're now going to do something different. Okay, we're going to do something better. Before I go there, though, just in the spirit of some open problems, let me just mention how in this old picture we also talk about loops. So we have a k-plane in k plus 4 dimensions. And for every loop, we kind of have a 2-plane. So there would be some, let's say at one loop, you would have some 2-plane L gamma A, which would be some its own matrix, D gamma A, Z A I. And if I have many loops, I would have many of these things. And the positivity condition that you're supposed to impose is not just that this matrix C is positive, but that you're supposed to stack this k by n matrix up at the top here, and then for any number of loops you have, you're supposed to just put them as an additional L 2 by n matrices to make a grand total of a k plus 2L matrix. A k plus 2L by n matrix. And what you're supposed to demand is that all the minors of this big matrix are also positive. But all the minors that involve C, as well as C and D together. I have to take the entire D block. Okay, so I take C and one of these Ds, all these minors could be positive. Or C and 2 of the Ds, all those minors could be positive, and I can take any subset of these guys and still have it be positive. Okay, so this is a real novelty. So independent of anything to do with the amplituhedron, this is just some extension of the usual picture of positivity that one is used to in the positive Riemannian. And it has this interesting feature that it involves a bunch of new objects that have to do with loops. And between these objects, there's no ordering. The notion of ordering is very important in positivity. If you're talking about minors being positive, you've got to order them in some way. But here it's not. Here, because these are 2 by n matrices, there's 2 of them, I can order these D's relative to each other any way I want, and the statement doesn't change. Okay, so there's a novelty associated with loops, which is a quite different sort of positivity than we've been used to, and you can already ask it at the level of positive matrices, okay, before doing anything else. You can ask, what's the analog of the Plabic graphs, what's the analog of the boundary measurements of the positive coordinates, all of that, before getting to any of the rest of it already at this level. And I will return to this in a moment. The dead simplest version of this problem that highlights the novelty actually gets rid of the C. So here's the absolute simplest version, is imagine general L, but n equals 4, and each D matrix I can bring to this familiar form. So saying that all the minors of each D matrix, so each D matrix is just a 2 by 4 matrix. Saying that all the minors are positive just tell me that all the X, Y, Z, W are all positive. But now I just want to stack any pair of them and say that any pair of them, any DI and DJ, is also positive. And that's all I can do. I can't even talk about 3 by 3 or 4 or any more of them, because already stacking 2 of them gives me maximal minors. Okay, and so that's just the space then. That's just the space of X, Y, Z, W positive. And this condition is just this very simple statement that Xi minus Xj, Zi minus Zj, plus Yi minus Yj, Wi minus Wj is negative. Okay, so that's it. So there's your new positivity problem. So it had one part that had an ordering in it. That's just the usual one we're familiar with G24 that says that all these variables are positive. But there's this other part that's totally permutation invariant. Okay? And this is the sort of real novelty. This is where the all loop information comes in. And the solution to this problem is equivalent to the solution of the integrand for 4-particle scattering to any number of loops. Okay, so this is one sort of very meaty, beefy part of the n equals 4 super-Yang-Mills problem. I'll come back to this towards the end of this lecture. Okay, so but that's something that I would love my positive friends to think more about. Okay? because it's really a different kind of positivity, and it would be really fascinating to see what we can tell you from years of studying this problem that despite the fact that, I mean, what is this? This is just a problem of, in the upper quadrant, I group x and y and z and w into vectors, so it's just a problem of saying I have like, I have A type of vectors and B type of vectors. I probably haven't drawn it right, but it's just the problem of saying that the line between any pair of A's goes in the opposite direction as the line between the corresponding B's. Okay, that's it. So I just have a bunch of points in the upper quadrant, and this is just saying that the dot product between AI minus AJ and BI minus BJ is negative. Okay, so I'm just throwing a bunch of points in the upper quadrant and demanding that, that the line between I and J for the A types points in the opposite direction as the line between I and J for the B types. We can tell you that trying to solve this problem is very challenging, but perhaps there's some combinatorial structure behind it, just like we saw for the positive Riemannian that we have not seen yet. But I'll say a little bit more about that. Okay, so, but all of these things live in auxiliary spaces. Now, the first thing I want to do is say what this, how we think about the amplituhedron directly in kinematic space. Okay, so the story is going to be slightly abstract at first. So really, but just to give a picture of what's going on, we have this big kinematic space. This big kinematic space is now just completely ordinary. Okay, just nothing extra, just the space of n momentum twisted variables. So the space of 4 by n matrices. I have an ordering. That's, as usual, that's the color ordering for the amplitudes. And now, somehow I want to tell you where the amplituhedron lives here. Where does it live just in this space? Naively, we don't have it. To see it, we needed these k-planes in k+m dimensions. We needed this, we needed this y. Where is all of that going to be? Yes?
Sorry, just a question about this.
Right.
I mean, are the D's supposed to be GL2 invariant?
Yes, they are. I just gauged.
Okay, but that's going to change the sign of the stack.
No,
right?
no, it doesn't. No. I'm asking for all the minors to be positive, including the minors for the of each D by itself. So once I fix all those signs, then I'm asking for all of them to be. I'm asking for them all to be mutually positive. So in other words, saying each D itself is positive fixes all those signs. So I'm saying that all the individual minors of the D's are positive as well as the stack ones. Okay. So what I did is then gauge fix so that, let's say, all the minors of all the D's are individually positive and the mutual ones are positive. So that's not a that's an invariant statement. In fact, we're going to be coming back towards the end of the lecture and talking about relaxing some of those signs or switching some of those signs around. But this is a completely invariant statement. Is that clear?
Yeah.
Okay. Okay. So I'm going to be looking for something in this space. Before telling you what the geometry is, let me actually tell you what we're going to be looking for instead of the scattering amplitude in this space. So this is as I said, it's the sort of central, it's very simple but sort of qualitative idea. So let me illustrate by first saying, for people. We know these things. Let's say we're talking about NMHV tree amplitudes. Let me write down a few formulas. So there's a formula, a super formula. If you haven't seen it, just take it on faith. But there's a super formula for a piece of an amplitude, which is the sum of a bunch of building blocks. Doesn't matter. There's some of the basic building blocks. But what matters is what these basic building blocks are, and a basic building block 1, 2, 3, 4, 5 is a super function, and it depends on the momentum twister data and these super variables. And every bracket here is just a contraction with an epsilon symbol. Okay, so the z's here, so this depends on 5 z's and 5 etas, and this is the explicit formula for it. Okay, so the first statement is that officially, naively, the amplitude is this function, the super function, depends on bosonic and these Grassmann variables. Okay, now how does the amplituhedron treat exactly the same object? The amplituhedron says this is actually, this is related to a canonical form for a simplex. I have 5 z's. Remember, as far as the amplituhedron is concerned, the z is 1 higher dimensional. So z has 5 components. So there's a simplex with the vertices 1, 2, 3, 4, 5. And so the conventional picture of the amplituhedron would associate with this thing some form for 1, 2, 3, 4, 5. That would be d log of y, 1, 2, 3, 4, d log y, 2, 3, 4, 5, and so on. 4 d logs, 4, 5, 1, 2, and then I can divide by one of them, any one of them I want, 5, 1, 2, 3. So there's a y in all of these things. Okay, and this d hits the y. This is the form in y space. Okay, so, and so the sort of jujitsu we were talking about before was that there's this way to go from this form in y space, and there's some procedure to go from this form in y space to this super function in z space. So let me make the first simple observation is that there's something much more natural that we could do. Once we have that object, is we could just let this, we could let the d hit everything. Let's say we hit, imagine we let this d hit everything instead of just the y. Okay, so we're also going to let it hit the z's. So that means that this form is a giant form, it has all kinds of pieces, some pieces where the d's hit the y's, some mixed pieces where some d's hit y's and some z's, and some pieces where the d's just hit the z's. Right? Now notice in the pieces where the d's just hit the z's, everything has a y in it. And so that piece is really a form that's not defined on the space of all the z's, but it's defined on the space of all the z's projected through y. So what I can do is take exactly the same formula, and if I want to see the piece that only has the dz's in it, I can just to begin with write down something else. So I can, to begin with, go from here, and instead write down omega that now lives on z space is, and these are now 4-dimensional z's. So maybe I should distinguish that I have the z's of the amplituhedron, I have these upper z components which are m components, and I have the rest of them. So there's a form that lives on this little z space, the ordinary momentum twistor space, which is just d log of 1, 2, 3, 4, over 5, 1, 2, 3, and so on. All right, so that's sort of interesting. Now we have a form on momentum twistor space. So now the sort of data starts matching up more between this side and the other. And in fact, this form is the superamplitude. Directly is the superamplitude. We have these Grassmann objects floating around. What do we know that are Grassmann objects? Differential forms are anti-commuting Grassmann objects. So this literally is 1, 2, 3, 4, 5. If you just take all the etas and replace them by dz's. Okay, so that's the first interesting observation, that scattering amplitudes are directly differential forms on the kinematic space. Okay. And in fact, their superness is just the fact that they are differential forms in the kinematic space. Okay. No more y's, no more extra components to z's. The amplitudes are just directly differential forms on kinematic space. Now, what is the gain? What is the gain of this? After all, you could say that a Of course, I could have always said, let me take this, let me take these super things, these etas or grasping, let me just call them dz's. What are we gaining? What we're gaining is that this equality is not, first of all, this equality is not totally obvious. Here I have something that looks like a bunch of d logs, and here I've written it, this is the sort of final answer. This doesn't look like a bunch of d logs. Okay. But it's true, this is an identity. And the point is, when I think of this as a function, I don't see any geometry. When I think of this as a function, I don't know how to take residues, I don't know how to sort of see geometry in the residue structure, in the singularity structure of the function. In order to talk about residues, I need to have a form. Okay. This is the form. This form, and this way of writing it says, this object actually kind of looks like it's associated with a simplex. It has logarithmic singularities in some interesting way. Okay. So it's not, this form makes it clear that what we're looking for are certain differential forms on kinematic space with logarithmic singularities. They're d-log forms directly on G4n. Okay? So let me summarize. So we're starting to get somewhere. Again, this is our kinematic space. These are, maybe I should have be uniform now, we'll call them little z's, sorry. So these are 4 by n. More generally, we could replace that by m by n, at least at tree level, but let me just stick with this case. And now, what should we be looking for at loop level? So at loop level, we're talking about the integrand. And we can think about loops as lines in momentum twistor space. So this space of 4-dimensional vectors, there's a natural rescaling of each column, which is the little group scaling. There's a torus action that rescales each column. So we can think of all the points also living in P3 sometimes, although in this lecture we'll really be thinking about them as 4-dimensional vectors, an action of the torus. But also, each loop variable is associated with a line in momentum twistor space. And so, what we're looking for is a certain differential form that the part that depends on k for the amplitudes is already, as we've seen, giving us a 4k form. Okay, so all of the Graspin stuff, all the super stuff, is in the fact that there's some 4k forms. And each one of these loop variables also has 4 degrees of freedom that goes with it. The space of lines in P3 is 4-dimensional, where each loop momentum variable has L0, L1, L2, L3. Okay, so it's the same counting. So there's some 4k plus L form that lives on this space. Okay? So that's what we're after. There's a 4 plus k L form, which depends on the z's and these lines. Okay? And so now we have our precise question. Now we want to find a question in the space of L lines or L2 planes in 4 dimensions, if you like, if I want to think about all these things living in 4 dimensions. L2 planes in 4 dimensions, as well as n vectors in 4 dimensions with an ordering. I want to find a question that's going to give me a 4k plus L4. Okay. So that's what we're after. And so let me just go back to a tree level now. So L equals 0. And let's now talk about what it is that we're looking for. And so let me give you the sort of broad outlines of what we're looking for first. Okay. So, and then I'll do a couple of examples. So, the broad outlines is now all I have are the z's. Right? Z1 to Zm, and again, I'll go back to the general. So in this space of n m-dimensional vectors, I can actually think of this as GMN, because I have an action of everything I'm doing has an action of GLM on it. Okay? So I can really think of this equivalently as just living in GMN. But in this space, I'm going to have an interesting positive part. The positive part is not going to be the usual positive part that we're talking about. It's going to be a generalization of the usual positive part that we talked about. And it'll be labeled by some k. Right, so first we have to talk about what this positive part is. And as we'll see, it involves not just a notion of positivity, but some extra topological notions as well. A notion of a certain winding number associated with the configuration of Zs. So you really imagine I give you n m-dimensional vectors, and there's a certain sort of topological way they have to look. Right? They have to have some particular winding number or a particular sign flip pattern in order to belong to this pk. Okay? So this is some sort of top-dimensional region in the entire GMS. Okay? So this is just some large region inside the GMS. Now, this space is naively m times n dimensional, or maybe if I'm modeling by GLM, it might be m times n minus m dimensional. But in any case, this is not equal to m times k. So we're looking for a 4k or an m times k form. Okay, so and in fact, we're looking for a much lower degree form than a top form in the whole space. So if you like, that's already one interesting question. Is you might want to know what's a collection of. There's a whole collection of forms probably that live on this space, which is interesting. And we're interested in one of a particular dimensionality. But this one is going to be characterized in the following way. It's going to be fully determined by the following property. I want to find some place to pull this form back to so it becomes a top form. Okay? So what I'm going to do is find a subspace. And this subspace is also going to be, or family of subspaces is also going to be n times k dimensional. Just not one, there'll be a whole family of subspaces that are m plus k dimensional. They will also have to have a certain positivity property. Okay? But now, the claim is that the intersection of this subspace with this big positive part is the amplituhedron, okay? Or is the sort of avatar of the amplituhedron in this space. In other words, if I'm localized to this subspace, then what I see on this subspace, first it has the right dimensionality to be the amplituhedron, and secondly, it's literally the amplituhedron, but with some particular choice of this fixed external data that I had before. Okay, so remember, in the story of the amplituhedron, we had some fixed external data that was m plus k dimensional, right? And when I fix that fixed external data, I sweep out some region in gk k plus m, right? So all of those choices of the fixed external data before is going to go into determining this subspace. So the big Z external data that we're used to, let me call it Z star because it's going to be fixed. And that external data is actually going to fix what this plane is. If I change the external data, I'll change the plane, but always the intersection of this plane with this positive part is going to look like the amplituhedron. And what is this form that lives everywhere? This form doesn't care about this external data, doesn't care about any of these things, it lives everywhere. But this form, the omega that we're interested in, this omega m times k that we're interested in, has the property that when I pull it back to that subspace, it becomes the canonical form for that amplituhedron. So I want to find a form that's kind of nailed by geometry. That's what we did before in the story of the amplituhedron. Now the form that we're interested in on kinematic space is a low-dimensional form in a high-dimensional space, but we're going to reveal the amplituhedron by intersecting some positive part I haven't defined yet with a family of subspaces. And when I pull this form back to that subspace, it becomes the canonical form for the intersection, which is how you see the amplituhedron directly in kinematic space. So, as I said, this sounds a little bit abstract here. When we do the bi-adjoint bi-cube theory in the next lecture, it's going to be a sort of much simpler example where it's easier to visualize what is going on. Here, everything is kind of a little fancy and curvy, but I want to talk about it first, not only because it was the historically first place that we saw this, but also because this is a case where we understand everything to all loop order. Okay, so this is at least an in principle complete definition of the theory of the planar limit. And once I tell you what these spaces are, in a moment we're going to be done. Okay, so let me now tell you how this works. So one way you can arrive at this picture, and this was essentially the motivation, is to ask the following question. This is just a brief motivation. Let's go back to the usual picture. Even for polygons. Here I'm drawing a projective picture here. I drew a non-projective picture. I have really some configuration of three-dimensional vectors and some vector pointing in the direction of y. Projectively, I can think about these things as living on the inside of a polygon. And I want to know the answer to the question, how do I decide whether, if I define y is the convex hull of all these points, how do I decide, if you hand me a y, whether y is actually inside the polygon or not? And for polygons, there's a very simple answer to this question. You just have to ask that you're on the right side of all the boundaries. So if you know what all the codimension 1 boundaries are, you're done. But this is famously not true once you get into the world of positivity for Grassmannians. Okay, so for instance, in positive G24, it is all the codimension 1 boundaries are when 1, 2, 2, 3, 3, 4, and 1, 4 go to 0. But it is not enough to just say these are all positive, because that would be consistent with two possibilities. That would be consistent with either 1, 3, and 2, 4 are either both positive or both negative. Okay, so you have to say that 1, 3 is positive, which then implies that 2, 4 is positive, but you can't just make a statement about the codimension 1 boundaries. Okay, and so the natural question was, well, what else do we have to say? What else do we have to say in order to be able to decide whether some point y is or isn't in the amplituhedron? And the answer turns out to be, and this is the answer that we gave with Hugh and with Yara, to think about what the configuration of z's looks like after you project through y. So let me do a simple example for n equals 2. So when we have m equals 2, again remember, our big z's are 2 z's and then some extra k components. Okay, so this is 2 and k. And our y is a k-plane in k plus 2 dimensions. But you can ask, what do the z's look like? If you have a point inside the amplituhedron, what do the z's look like after you project through y? You literally sort of project in the direction of y. After you project through y, now we have a two-dimensional picture. Y has gone to the origin. So y has gone to the origin of this two-dimensional picture, and I have a bunch of z's. Okay, now you can ask, what does this configuration of z's look like? Okay, and so already you see, and already in the simplest case, k equals 1, let's say we do, we could do k equals 0 as well, but let me just start with k equals 1, because in k equals 1 was what we normally think of as the polygon, right? So, but now we'd have a three-dimensional vector we're projecting now onto this plane, so we would normally think about it the inside of the polygon. Well, what does it look like? What it looks like, how do I decide that this is what the configuration looks like? I just have to say that all of these vectors are sort of winding around the origin in the same direction. So I have to say that all of these I plus 1s, so these are now the sort of minors that you'd make involving the this two-dimensional data now. So all these I plus 1s are positive, and now this, in this case, I really mean n1 is positive. So we're familiar with the fact that sometimes there's a twist. But in this case, I really mean n1 is also positive, not 1n is positive. So there's that, but not just that, because if I just said that, that would be compatible with a picture that doesn't look like this polygon. It could sort of go around and wind around many times. So you also have to say that this thing, which is this path, which is the sum of all these segments, I plus 1, this path has winding number 1. And so that is what the region looks like that's compatible with starting from positive external z's that are three-dimensional with y inside the amplituhedron and projecting through y. Okay? And in fact, for general M, for general K, sticking with m equals 2, in this example, you can also see that if you're winding around like this, there's another way of talking about the winding number, which is sort of even easier to check on a computer, or if you're blind, you couldn't see the picture and check what the winding number was. I can, for example, take this point 1, and I can look at the line passing through 1, and I can just ask that this path crosses this line exactly once. That's what it means for it to have winding number 1. Okay, so this simple topological notion of winding number is also associated with the even simpler notion of winding number if I project further through 1 and go down to a one-dimensional picture. So that's what I'm doing here. When I go down to a one-dimensional picture, now 1 and everyone else is at the origin, so everyone I'm asking to just flip around the origin exactly once. Okay, so this notion of winding number in 2 dimensions is closely related to the notion of sign flips in 1 dimension. And so this is equivalent to saying that this sequence 1, 2, 1, 3, blah, 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 up to 1n has 1 sign flip. And you see, so long as everyone is winding around the same way, so I could say this as a sort of cleaner, as a more symmetric statement, that I just have everyone, all these I plus 1s positive with winding number 1, or I can say it as a more efficient statement, that all the I plus 1s are positive, and I just pick one of these sequences, any one of them. It doesn't have to start with 1, it could start with 2, it could start with any one, but the sequence 1, 2, 1, 3 up to 1n has 1 sign flip. Okay? Now, all of these things generalize for all k and all m. And let me just cut to the chase. I can tell you what the symmetrical winding number description is, but the fastest description is the following. The analog of this sign flip description is the following. And so the claim, I think this claim is not proven. So we don't have a proof in general. I think there's a proof for n equals 2, for m equals 1 and n equals 2, but anyway, it's true. The claim is that that the amplituhedron is entirely characterized by the following properties. Let me just do it for m even. There's there's a similar story for, well, I'll just say it for m even. The analog of all of these pieces winding around in the right direction are just that I plus 1, I1 plus 1 up to I m halves plus 1 are all positive. So for example, for n equals 4, these are the people who know about cyclic polytopes know that these I plus 1 jj plus 1s are very natural objects. They're the simplices that are the boundaries of the cyclic polytopes. So this I plus 1 jj plus 1 structure comes up all over the place in this business. But again, this is not enough. This is just saying you're on the sort of right side of all the boundaries. On top of that, you have to have that this sequence plus this sequence, and the efficient way of saying it is just 1, 2, 3 up to m minus 1, m. 1, 2, 3 up to m minus 1, m plus 1, blah, blah, blah. 1, 2, 3, m minus 1, n. Has k sign flips. That's it. So that's a two-line definition of the tree amplituhedron. Okay. What's the definition at loop level? So remember, at loop level, we also have these extra lines, AB. So it's the most natural thing. You have this extra line, so you can further project through this two-plane in 4 dimensions and go from a 4-dimensional configuration, let's say, to a 2-dimensional configuration. So let's now stick to m equals 4. So now I'm going to do loops. So this is the tree amplituhedron for any m. Now I'm going to do loops. So here I'll just stick to m equals 4, even though there's a generalization again. But let me just leave it at this. So I additionally have these loop two-plane in 4 dimensions. So I'll call it AB. So for each one of them, if I have just one of them, but for any one of them, first, when I project through that guy, it has to go back to the 2-dimensional problem. So all of these things have to be positive. And the sequence AB, 1, 2, AB, 1, 3, up to AB, 1, n, should have k plus 2 sign flips. And last but not least, I can project one line relative to the other line, and the lines should all be mutually positive. That's it. So this half board is the entire definition of the amplituhedron. It's all loop order. These funny numbers, k and k plus 2, are actually maximal in a precise sense, but I won't say more about that. So they're not even arbitrary. You can't have more sign flips than this in a after I say something else. Okay, so this defines in this. So now we're back to our picture. Okay, so in this space of z's and ABs, this now indexed by k defines my kind of positive part. Okay? Now I have to tell you what this subspace is. And the subspace is just going to be 4 times k dimensional, or m times k dimensional. So this part doesn't depend on the loops. So this is just going to be this m times k dimensional subspace. So who is this subspace?
So here I have some question.
Yes.
So for the claim, do you have some results or some guess for MR?
Sorry, for what?
For MR, for odd number.
Oh yeah, it's exactly the same. Yes, for m odd, it's just the only thing which changes is that the so let me actually write it here because the flip part is exactly the same. For m odd, you just have to check 1 I plus 1 jj plus 1 blah 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 is positive, and I plus 1 jj plus 1 blah 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 n is positive. So there's this funny even odd thing associated with the cyclic polytope, that the boundaries look like I plus 1, jj plus 1, etc. when m is even, and 1 I plus 1, jj plus 1, and n I plus 1, jj plus 1 when m is odd. So the cyclic polytope isn't really cyclic when m is odd, but it is naturally cyclically invariant when m is even. So it's just, these are the sort of obvious boundaries. Okay, so this is the analog of being on the inside of the polytope. But beyond that, you need this extra condition, and the extra condition is this topological winding number condition, which we've reduced to this statement about a sign. Okay, so let me finally describe what this subspace looks like. Sorry. So I don't know what the official names of this kind of subspace is, but all we're doing is we're looking at all the z's, all those little z's that I can get, that start from some starting z, and I'm just going to translate. So this is some m plane in n dimensions, right? So this I now runs from 1 to m, 1 to 4 in our case. So I'm starting from some particular point z star, and I'm translating in the direction of some particular k-plane in n dimensions. Okay, so my z, all the z's on the subspace are just a linear translate of this point. So I would write everything that I can reach as z is z star plus, let me write it as y alpha I, some delta alpha a. Now alpha is going to run from 1 to k, and that parametrizes this. So I pick a particular k-plane in n dimensions, and I'm translating this m-plane in n dimensions in the direction of this k-plane in n dimensions. Okay? So this gives me some subspace in the space of all z's. Okay? Some m times k dimensional subspace in the space of all z's. Right. And notice that, so how would I specify the data for this subspace? Well, to specify the data for the subspace, I just have to give you the z star. So here's the z star. So this is my m by n starting point. And I also have to give you this k by n matrix. So this is my delta. So just the data that labels the subspace is a k plus m by n matrix. Now remember, that was the data in the conventional picture of the amplituhedron. It was exactly k plus m by n matrix. Back then we were thinking about it as some fixed external data. Now our data lives in 4 dimensions, in m dimensions, right? This is instead a choice of a subspace. And notice that this subspace is not uniquely defined. Of course, I can translate z star by any amount in delta. So what I really care about is this whole plane. Right? I can do GLK, I can do GLM transformations there, GLK transformations there, and also translate this guy by that guy. And so we're going to demand that my positivity condition on the subspace is simply the same one that I had before, that all the minors of this matrix that now I think as specifying the subspace are positive. All right, so now that finishes the story, at least defining what we're talking about. I have the positive part. I have this m times k form that lives everywhere. I have this family of subspaces, not just one of them, but a whole family of positive subspaces that are m times k dimensional. And the intersection of this family with the positive part, the claim is the amplituhedron. Okay? And the pullback of this form to this subspace becomes the canonical form for that amplituhedron. So that's what defines the amplitude. That's what defines this form. Okay, so and at loop order, nothing changes. Okay, because then I just have L extra variables, my form is 4L higher dimensional, I'm still pulling back to the same subspace, and I should still find the canonical form for the amplituhedron that's revealed on that subspace. So my positive part changed. I defined these extra positivity constraints and winding constraints involving the loops, but the story of the subspace did not change. Okay, so this is the definition directly in the kinematical space for the kind of question that's giving us the answer, which are the amplitudes right equals 4 super ignorance. Okay, any questions about this? Okay. Oh, sorry, just to say the obvious thing, what is the direct connection? What is the direct connection? If I imagine this data, if I fix this plane, what is moving around in y doing here? It's exactly what I would get if, back in the original amplituhedron picture, I kept the external data fixed, I moved y around in the amplituhedron, and then I projected through y to see what my m-dimensional picture was. Okay? So the m-dimensional configurations that I get as I move y around the amplituhedron, then project through it, are exactly moving around on this subspace. Okay? So that's the sense in which what I see on this subspace is exactly what I was seeing before in GK K plus M. But now I see it all directly in the configuration space, right where it should live. Okay, now, as I said, it takes a little bit of getting used to, but I just want to pause for a second and just so we can absorb the claim, because I think it's again quite important. We're starting from an apparently arid and boring place where nothing is happening. M-dimensional vectors, right? And 4-dimensional vectors. That was our kinematic space. That's where somehow in that space we have to find a question whose answer are the amplitudes. And all we have, the only beginning clue we have is that there's an ordering. So we have this ordering, and that ordering begins a cascade of events that allows us to define all of this. So we can define these, with that ordering, we have a natural notion of winding, which gives us a natural notion of positivity. That gives us this notion of a positive part. Oh, by the way, if I ask that this subspace, if I start with a z, which that satisfied that it came from one of these, that I could uplift it to a matrix by adding a delta where all the minors are positive, then the windings that you get are maximal. The windings with the sign flip patterns that I talked about cannot be bigger than the one that I defined. So they're not random numbers, that they're winding around as much as possible. Okay? So now I'm looking for a lower form, and so, well, that's what I have to do. I have to somehow find a place that nails this form by some singularity, and so I find this family of subspaces that I intersect with this positive part. And the requirement that the form has logarithmic singularities on this object, the claim is completely fixed. Okay, so now, let me say, so that's the definition. Let me now just say a couple of open problems, and then we can. Let me go 10 minutes. Are you the boss, Lauren? I'm the boss, right? All right. Big mistake. All right. Okay. So let me say a couple of open problems. So I mean, apart from sort of proving many things, but some new open problems. Okay, first, before doing anything else, there's a completely obvious question. We already saw it in the simplest case where we took like 1, 2, 3, 4, 5, our usual friend, and we wrote it as a form. We recognize this as d log of 1, 2, 3, 4 over 5, 1, 2, 3, d log 4, 5, 1, 2 over 5, 1, 2, 3. Okay, so let's say I had n equals 6, just for 5 minutes. Doesn't matter. The full tree amplitude would be this sum, this 1i plus 1 j plus 1. So it would be 1, 2, 3, 4, 5 plus 1, 2, plus 1, 2, 3, 5, 6 plus 1, 3, 4, 5, 6. So it's a 4 form. It's a 4 form on G46, right? So this is a 4 form on G46. And so you see something a little interesting has happened because we know that in general, on the left-hand side, I mean, this is an extremely simple example, but in general on the left-hand side, we have some cell in the positive Grassmannian GKN, and it's a 4K dimensional cell. And now we're saying that this is inducing, this 4K dimensional cell in the positive Grassmannian is inducing some 4K form on the space of external data, some 4K form on G4N. Okay. Now, normally, we would get these things, the entire story of on-shell diagrams of the positive Grassmannian and blah, 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 is all about, we find this cell, so let me say this a little more concretely. Let's say precisely what this form is. So, you find so pick a 4K dimensional cell of GKN. Pick your favorite positive coordinates for it. They're not unique, you can have many positive coordinates for it. So this is some way of parametrizing some k by n matrix in terms of these 4K variables positively, so that the minors that are non-zero are manifestly positive. And there's a d-log form on this facet. Okay? And so what we're doing is we have to solve this formula that C dot Z, maybe I should call these coordinates x1 through x4k. There's too many alphas. So the entire story of the positive Grassmannian tells you that you choose this cell to be 4K dimensional so that you can solve these equations in principle. That C dot Z equals 0. Okay. So if you give me generic external momentum twisters, I can solve these equations to determine the positive coordinates for the x's in terms of the z's. Okay, so this gives me, so I literally solve for the x's in terms of the z's. And what I get from here is d log now of some x1 that depends on z's up to d log of x4 that depends on z's. So we've done that in this case. I've just already given you the final answer because it was so simple to do in this case. I've given you the answer in terms of the z's, but each one of these was actually just one of the positive coordinates for the G1K cell in this case, evaluated on the solution to these equations. Now here's a remarkable observation, which is also very, very closely related to the statements that James Drummond and Mark Sprouton and other people have been making recently, that some cluster structure begins to appear. I have not said anything about cluster algebras or anything like that yet. In fact, for this entire story, I could have just talked about the positive Grassmannian, ordinary positive coordinates, without ever knowing about the rest of these non-planar quivers or anything other than Playbit graphs. Okay? Okay, but the interesting claim is, and this is something we're discussing with Song and Thomas and a variety of other people, just starting to explore, is that these positive coordinates are actually turn out to be ratios of cluster variables of G4n. Okay, so this is a connection which we could have talked about, and we've been thinking about forms rather than functions that we really could have talked about already when we were talking about the positive Riemann, and just on-shell diagrams, nothing else. Okay? Now that we're thinking about forms, it's natural to just ask for what these, to solve for these positive variables in terms of the z's. Now, in this case, they're rather trivially ratios of cluster variables of G46. Okay, because these are just minors of G46. It's actually, it seems to be observationally true, although it needs to be checked in a lot more detail and more examples. Not only are these things, are these arguments, not only are they ratios of cluster variables, but the ratios of cluster variables that are compatible in some cluster together. They're not random ratios of cluster variables, they're ratios of cluster variables in G4n where the variables belong to the same cluster. Now, so far I haven't seen anything particularly clustery in this case. They're just minors, right? Because G46 is the same as G26. But immediately, you know, let's move on to n equals 7. In fact, let's just take n equals 7 for any k. First, for any n, for k equals 1. For k equals 1, what we ever see are these just this object, and so d log of ratios of minors. But already when we go to k equals 2, we're going to get some new objects. And from physics, we know immediately what those new objects are. For example, for n equals 7, k equals 2 is the parity conjugate of k equals 1. So we're going to get exactly the same kind of objects, except we're going to get parity conjugates of these minors appearing instead of the minors themselves. And beginning with n equals 7, parity conjugates of minors are not minors anymore. Okay, parity conjugates are the minors under the twist map. They don't go to minors anymore. They go into more complicated objects. Okay? In fact, those are all the things that we're going to get. If we do this for n equals 7, if we look at everything we see for k equals 1 and for k equals 2, we'll get ratios of both minors and parity conjugates of minors. That exhausts everything in the cluster algebra of G47. Everything you see in G47 is either a minor or a twist of a minor. Okay, but already we see something beyond, we see something clustery in the nature of the kind of d logs that make an appearance here. And again, it appears that not just that they're d logs, but that they are d logs of things that are cluster compatible in the G4n sense. So let me say again what the correspondence is that's now worth trying to establish is there's some answer to this question. Just take every one of the on-shell diagrams, every one of the Yangian invariants, all those things that we talked about before, they all induce some form on G4n. All the positive coordinates of the associated with GKN are expressed as ratios of certain functions of the variables in G4n. Are they cluster variables of G4n? Which subset of the cluster variables are they? When we go to a higher n, we clearly get a finite list of objects from these things. We know, as we'll talk about later today, that the cluster algebras can become infinite typically as we go to a larger n. So we're getting some finite subset of all the things that we should encounter if this correspondence with the clusterness indeed continues.
Do you think you'll continue to get flippers and twists of flippers?
No, you probably get more new things beyond that, almost certainly. So that was just saying. So that's just saying that this map now brings to life something beyond ordinary Playbit graphs in the Z space. Okay, so that's open problem number 1, is to just understand this connection. Okay, so take every. So this is, if you like, the sort of last chapter of this book. Okay, is that now we want to see when we take every one of the on-shell diagrams, it should induce some structure on G4n, and it seems to be related to some cluster structure on G4n, and what does it look like? Presumably it's true for any n. Okay, I have 2 more open problems, but maybe we should take a break, and we'll come back and start with them. Okay? When should we come back? You guys want to? How big a break do you want?
20 minutes.
20-minute break?